Okay, ready to start. This will be the fifth and final part, sadly. Sad to see the course end so quickly. I'm on part 5, planning and information spaces. I have a brief part after that. You might remember the previous part, which was planning with perfect information, where you have sensors that can measure the complete state. I just want to give you a bunch of examples here, some of it from our research, some from other research, where there's planning occurring in an information space, right? So information comes from sensors, and you cannot fully reconstruct the state. I gave one example, well, I gave some general ideas last time, which were just giving an overview of information spaces in terms of planning with regard to temporal filters. And I also talked about general planning issues. You might remember that I mentioned that there were predictability, reachability, optimality, and computability. So those are the things I went over. And now I just want to give some different kinds of examples. They're fairly disjoint, they're just different kinds of examples. And I don't think they're completely satisfying in the sense that there are many, many more things one can do with this kind of information space-based approach by starting in this direction. But I just want to give some examples so that you understand what we're talking about when we do planning in this way. So visibility-based pursuitivation was one of those examples. As I said, I went over that before, and people in this group certainly know this problem well. And for visibility-based pursuitivation, one of the key ideas was to not reason exactly about the location of the evader. We don't make models about it. We just say the evader can move arbitrarily fast. And so that is the beginning of minimalism. That is the beginning of trying to avoid estimating the state, right? You do not worry about the location of the evader. You reason about the set of possibilities in a combinatorial way. So that was the beginning of pushing in this direction. But we should still feel guilty about it somewhat, because the works that we did, some of these up here that I show, some of the original works that we did with people at Stanford, and later some of the work I did at Iowa State with Boris Simov and Gyora Slutsky. You may know some of these with one flashlight or two pursuers with one flashlight each. Pay attention to the fact that these still assume that you have a perfect mapping, right? Somebody gives a perfect environment description. They give a polygon. And if you're going to use these strategies on a robot, you then are assumed to have perfect control and localization. The robot moves exactly like you said it would, with exact geometric coordinates. So we did a couple of works after those to try to do pursuitivation with less information, where you are not given the environment. One of these is called, one of these uses the gap sensor. So it's pursuitivation using a gap sensor. So you still have visibility in the sense that if the evader is in the field of view, the game is done, but you have a gap sensor and you command the robot to move in terms of gaps. We also did some work. We have a very simple wall following robot. The idea there is inside of a polygon, inside of a simple polygon, we have a robot that can follow walls. So it goes moving along walls, but if it comes to a reflex vertex, it can do one of two things. It can either go this way, or it can continue onward until it hits another wall. So just very simple primitives, and we made a pursuitivation algorithm for that problem, and then we studied how much additional information do you need to give so that it becomes as powerful as the complete algorithm here for 360-degree visibility. In other words, it becomes as powerful as that pursuer. And you need to add a little more information, but not too much more, it turns out. So, and if you don't have that information, then the pursuer is weaker, but it can still do an interesting job. So these are a couple of papers you might want to look at. I'm not going to cover those, but they involve taking pursuitivation and reducing the information requirements further. Let me talk about searching a maze. So this is a very important kind of problem, very basic for robots. Searching is the problem of, let's say, looking for a treasure. So maybe you're on some kind of maze, and I say, there's a treasure somewhere, and you can only see the treasure when you're standing on top of it. You could make a visibility-based search. That's simpler than pursuitivation, right? It's like an evader that doesn't move. Right? Okay? So let's suppose that we have white tiles and black tiles. So we're moving around on a space of tiles, right? And if we do that, it should be somewhat straightforward to make a robot that goes searching. So we can make a very simple movement model. We can give these actions to the robot. We could say, you either rotate 90 degrees counterclockwise, so you can go like that. That's one command you can give to the robot. Another command is take a step forward. If you try to take a step forward and you instead hit the wall, so if I'm here and I say go forward, I hit the wall, right? Let's assume that we have a sensor that tells you you hit the wall, and you did not actually move, right? So that's what I want. I have that kind of simple sensor. So if I put you if I put the robot here on the collection of white tiles, and notice that the robot is always pointing in a direction, and there are one of 4 different directions. So the way to look at the state space for this, I can say E is a set of white tiles. And it's a bounded and connected set of white tiles. So I do not want white tiles that go off to infinity, and I want the set to be connected. All right? So that's what E is. It should say connected there. So maybe fancy E is the set of all of those, right? So I don't know what it is initially. It could be simply connected, multiply connected, whatever. And then this is the way the state space looks. This part right here, Z, Z, D, that is almost looking like this. Almost looks like R2 cross S1, which I could write as R cross S1. On the grid, instead of real numbers, we use integers. So there's integers, and then instead of S1, we only have 4 directions. So that's what D is. D is just up, down, left, and right, or north, east, west, south, probably. Probably best to refer to it that way. It's like a global frame. So north, east, west, and south are D. So that's all this looks like. This looks exactly like our formulations from before, right? Just on a grid now. Well, can you think of a plan that systematically searches all of the white tiles? Is that an easy problem? What do you think? I'm not being tricky here. What do you think? Is it an easy problem?
Yeah.
It's an easy problem. Good. Yeah, that's right. Just do some kind of breadth first search and build a map of where you've been, right? Let's assume the robot has a good-sized brain. So it can, a simple algorithm of just graph exploration, kind of online graph exploration, perfectly fine. Notice that you can easily recognize when you've come back to the same place again, because based on where you started, you can build a coordinate system, right? And keep track of like the I and J coordinates, let's say, of where you've been. So it's very easy to do that, and anytime you have tiles that you haven't explored, you can go from there. So let's think about that. So let's think about information spaces for this for a minute. It's very helpful. I think this example is kind of cute for that. So the information space could be that. It could be the power set of that, right? In other words, I don't know what my configuration is. That's position and orientation here. And I don't know what the environment looks like, right? So if you try to represent that directly, my guess is that it would be difficult, right? But sometimes, and the reason why I have this example is because I want to show you that sometimes having a very compact encoding of the information states is exactly what you need. So I can represent sets in here, this power set, but I do it in kind of a clever way as follows. If I've been on a white tile already, then I mark it as white. If I've tried to go into a black tile, and I notice that it's black, I mark it black. Yeah, I think my example should work like that. There should be some interior ones that you could never see, right? And then I have these are gray, let's say. For the gray ones, they're called unknown here. That means I have no idea what this is, right? So now you can make a very simple method that just says anytime you see these gray tiles, you try to move for them, right? You just try to go and hit all of the gray tiles, doing whatever simple strategy you want. There's many, many ways to do it. I don't care what's optimal. If you do that, try to convert the gray tiles into white or black, and then do that until you can't do it anymore, then you're done, right? You have guaranteed that there's no treasure, if you want. Just like you guarantee that there's no evader when you solve the pursuit evasion problem, in some sense. Does that make sense what I'm talking about? So the information space here is considering these different ways to partition Z cross Z into white, black, and unknown tiles. That's how we're considering that. This is the way the picture looks for each one of the information states, right? These are the information states we can describe, and they're exactly relevant to the problem. Okay, I'm not going to use the wireless here, but my laptop is very eager. Let's see. And so, are there any questions about that? Does that make sense? I'm trying to make it so that it starts off looking kind of complicated, but by cleverly just shading in which ones are gray and which ones are white, you can represent this. You may have another, you can imagine other versions of this. Maybe we have a computational geometry kind of representation, like a cell decomposition. And maybe there are gray cells and black cells and white cells. You can do it any way you want, and you go exploring in an online way. And this is just kind of the way it might look for a map building robot. Right? It just characterizes the unknown frontier, and that's how we represent these elements of this power set, right? All right, so that's the idea for that. How much memory is required? Well, the filter, there's a filter running here. The information state of the filter is this picture. White tiles and black tiles and gray tiles. And of course it does not need an unbounded collection of those, right? It only needs enough to enclose the white and black tiles and gray wherever you haven't seen. So this does not even need to be represented. It just needs to keep track of a little bit around where you've been, right? So that's how the information state looks. The amount of space you're going to need is linear in the number of white tiles, correct? Now, it turns out that way, way back in ancient times, 1978, there's a paper by Manuel Bloom and Dexter Kozin. It's called something like The Power of the Compass. And it's very interesting. It shows that for this problem, they can solve it using only a logarithmic amount of memory. You only need to remember as much information that's logarithmic in the number of white tiles. How can that be, right? So it beautifully encompasses exactly what I'm trying to say here, is that for the task of systematically searching the environment for a treasure, you do not need a perfect map. It's sufficient, but not necessary. So these clever guys, they figured out that all you need to keep track of is your latitude. It's like one integer that tells you how far up or down you've gone, relative to where the direction you started as you've gone. And then 2 bits, they keep track of your orientation. That's the D element here. Except that one's global. You can make it all relative to where you started, so that's fine. There's always this issue of local coordinates versus global coordinates that are very important for robots, right? A robot might not know what direction it is pointing. Not a problem here because you were not given the map anyway, so you can make up your own coordinates. Anyway, they did this really, really clever algorithm. I highly recommend looking up this paper. It's very beautiful stuff. Very nicely written, the first half of it. The second half of it's much more, somewhat intense. They make very bizarre connections to differential geometry. They have the Gauss-Bonnet theorem and all kinds of interesting things in it. But the first part basically just does this. They figured out that with this model, you can detect you can arbitrarily pick some place inside of each hole, let's say, for each obstacle. Sorry, each one of these are obstacles. For each obstacle, you can find what's called the southwest corner. They define it very carefully, and they show that you can detect the southwest corner. And then what you do is you pretend that the southwest corner is connected to whatever's below it. So then it makes the environment appear to be simply connected. And then you just go around the environment in some kind of zigzagging fashion like this to cover the whole thing. And they prove very carefully that they can get away with doing it systematically without ever having a map and guaranteed to cover all the tiles. So I'm not covering the details of their method, but it really beautifully characterizes it. So the information state in their filter, they will not use this terminology. This is from a long time ago. But their information states are just latitude and orientation. Very clever, right? Bloom is a Turing Award winner, by the way. He's at Carnegie Mellon right now.
Can you read the guidebook invested for the medial axis?
Medial axis.
In 1967.
Wow. I don't know if it's possible. I'm not sure of that. Anybody else know? Right. I talked to you about, are there any questions about that? So, that's pretty cool, right? I think that's interesting stuff. That exactly gets into what I want to do. How small does the filter have to be? Only logarithmic in size. Very nice. Okay, gap navigation trees. I've talked about gap sensors, I talked about gap navigation trees last time in terms of filters. But now I want to make them active. I want to use them for planning. I think last time I went a little too far, and I did explain a little bit about how to use them for planning because people were asking questions. But I'll go back over it again. So this is what I showed you before. You can learn the shortest path tree. It looks like this to the robot. This is how it would be embedded in the environment if the robot could see the environment, but it can't. This is how it looks from the robot's perspective, sort of, but the robot does not even get these distances or angles or anything. And so what we want to do when we put in planning is we have that filter running, and we have two kinds of tasks. One of them is fully exploring the environment, and another one is doing distance optimal navigation to some place where you've already been. So number one could be called the learning phase, and number two could be called the task execution phase, if you want. We have this in Transactions in Robotics 2007. So we have a new primitive now. For the filter, you can just imagine that the filter's running, the robots can just randomly move around, and the filter produces the gaps in these trees. Okay? But now I want to give a command to the robot. The command is called chasing a gap, gap chasing. So if it has a gap in view, it can move directly towards it. So if there was a gap, if the door were open, there would be a gap there, and I can just move directly for it. That's the way it looks to the robot. It doesn't have exact measurements of distance or anything like that, or angle, but I'm just assuming it can do some kind of sensor feedback motion to go directly there. Right, so let's assume it can do that, and it moves on a straight line when it does that. Then here's what's going to happen. When it gets to that gap, there's two possibilities. Either the gap splits, because it's going to be coming up on what's called a bitangent that you might know from Pursuit Evasion, or the gap's going to disappear. It disappears when you do something like this. I think I have a slide for it anyway, but let me just show you. So if this is a gap here, right? So, oh, I'm sorry, that's not a gap, that's the inflection line. If I'm here, I see a gap, correct? So when we start moving this way, the gap disappears, correct? Right? So that means that, oh, that's exactly it. It disappears because we get to the end of the corridor and we see everything. Right? So if I chase the gap, I'm going to be moving like as follows. If I chase the gap, I'm going to be moving like this. Right? And then when I get there, on the corner, it'll be a critical case and I'll see everything. I'll assume that I can sit right outside the corner and see everything. All right? To really make this clean, you need to put an epsilon around everything and be a little bit careful. It won't matter too much here. All right. So here's the deal. I will take a gap, and if it ever appears, I will call it a primitive gap. Anytime a gap appears, for example, if I'm over here and I'm moving for some reason, let's say like this. Now that cannot be true for this kind of motion I just described. But if I move in this direction here, like this, when I get over here, a gap will appear, correct? I'm going to call it primitive. Primitive means, let's say, not divisible, like a prime number. Right? The reason why I'm saying that is because if I were ever to chase that gap, what's going to happen? Can it split? It can only disappear. It cannot split. That's why it's primitive. I need to go around and figure out which gaps are primitive. It turns out that once I've done that, I've learned the environment. I've learned the environment. Right? So that's the idea. So here's how to do it. You just mark all gaps in the tree as non-primitive initially. So I initially just have my gaps. I call them all non-primitive. And then I just keep chasing any gap that is a non-primitive leaf. And if it disappears, I go to step 6, increment K, keep going. I don't know what K is counting here exactly. It's not too important. So I go back to step 3 and I keep chasing. So if it splits, then I pick one of its children to chase. And I keep chasing and chasing and chasing. I go down the family tree until I find a child that disappears. When it disappears, I'm done. Right? Okay, this fear will be good. Kind of getting spooked out. Who knows? All right, so that's the idea, right? You keep trying to chase and split until you get to a node that disappears. Then, when you go somewhere else, that gap will reappear, but it'll be primitive, right? So that's the idea. Force anything that might be splittable, you try to split it. When you're done, you will get all the leaves of the tree to be primitive, and that means that the environment has been fully explored. Here's a very simple example. So this is how the gap sensor, the gap navigation tree looks initially like this. And then I chase gap A. When I chase gap A, C appears, correct? I put a box here to denote primitive. So now I go here, I'm following A. That's how it looks. Oh look, C and B merged. So if C and B merged, I write it like this. I have new gap D and C and D are merged. Then I start chasing D. Why? Because I notice that it has non-primitive children. So I need to go there and investigate. So I chase D. At some point, D will split back into C and D again. I already knew that would happen. And then when it does, I chase B because B is non-primitive. I go there. When I get there, I just get A and E. E will appear, and all of this disappears. I forced B to disappear. That's fine. So once I get to this means I'm done. There will never be, no matter how much more I move around, there will never be another split that surprises me. I know all the primitives now. Now, of course, I have A and E here, but I don't have C anymore, but that's okay. It will, if I move over there, it'll come back again. So this is the way it looks. This is just the shortest path tree, right? It's just this part. If I go back to the picture here, it's just this tree here, right? From the location where the robot happens to be standing. It will adapt itself as the robot moves. And now, if you want to get somewhere, so that's how you learn the environment. If you want to get somewhere, oh, you might remember I showed you the video of this last time, right? It showed a robot going around in the polygon and it learns this tree. Now, if you want to get somewhere optimally, you just extend the model a little bit. You put an object, let's say a triangle here, in the environment, and then anytime you can see the object in your field of view with a camera, whatever you like, you say, oh, that's an object that I'll record. And then if it disappears behind a gap, then I just keep track of which gap it disappeared behind. Okay, so then eventually it might bury itself down here, because it'll disappear behind a gap, and then that gap will merge with another gap, and then that gap will merge with another gap. So it just is buried in a tree somewhere when you're far away. And if I want to get to that object optimally, all I do is chase this gap, and then chase this gap, and then chase this gap, and then chase this directly. And that will be, we proved, the optimal path possible out of all possible Euclidean paths to get to that object. So it's the shortest path to the object, but the sensors can never measure distance. I think it's pretty amazing, right? So, because it learned exactly this kind of computational geometry object of the shortest path tree. So that's the idea. When you chase A will split into C and D, but then you'll get D and then you chase F, right? And over here it shows the chasing of, then when you chase F, it'll split into G and this. That shows that there. Right? Eventually the object will become visible and you go straight forward. So that's how you use this kind of gap navigation tree filter for planning. Remember, this is how the environment looks to the robot. You cannot distinguish between all of these cases. They all have the same tree, but guess what? Who cares? If your goal is only to do distance optimal navigation, which is an important goal, then the robot never needs to learn what the difference is between these. It just needs to know that all of those are encoded like this. Because that's the right encoding for doing shortest path navigation, as you kind of know from shortest paths and polygons. Right. Any questions about that? It seems to happen over and over again that we find some kind of structures that computational geometers already know about. Because very often they're trying to reduce the complexity of their algorithms, and they are also doing some kind of minimalism, like trying to figure out what information you actually need to compute with to get the solution. That turns out to be very closely related to what robots need to sense in order to navigate and solve their problem. So very similar philosophy. Yeah?
If some irregularities or noises are present on the edges, so there might be small leaks.
Yeah.
Then how can we filter out these irregularities?
If you add noise to this, then you have to do some kind of analysis of noise, right? Think about the possibilities. I think if your environment remains simply connected like this, then it's not so bad, but I'm telling you that if you want to navigate in this way, your system needs to be able to reliably get gaps and chase them. If you want to make a model of how far away you can deviate from that, in terms of probability of errors, metric distances, now you add a lot of geometric error analysis into it. And then, it depends on the model that you have for that, right? We implemented it with real robots. It seems to work okay, but there's also troubles. If you use a laser scanner, it may be difficult to sense a gap if it's very, if the laser scans are such that the wall is maybe kind of far and the laser is close to parallel to the wall, then the distance measurements get far apart, and they may look like artificial gaps. So that's an issue. There's a group at Oxford University, Liz Murphy and Paul Newman. Paul Newman's a professor at Oxford. They made a version of gap navigation trees with limited depth, which is also interesting. So I think there's a whole family of things you can make. You might remember that the gap sensors I defined in the first couple of days have both fat gaps and thin gaps, all these different types of gaps. And so those are all open problems. What kind of navigation strategies can you make with these different types of gap sensors and filters based on those, and a lot of open questions. But you can always make noisy versions of these too and ask questions like that.
We should reduce the sensitivity of the gap sensor so we can deal with some
maybe.
local irregularities.
Yeah, that's right, to try to understand. We also made a version of this where there's holes in the environment, and now you need to be able to distinguish between different holes and to know that you've gone around the hole. Those are two different things you need to sense. If you do not, we prove that you cannot optimally navigate. Actually, and in that case, you still can only optimally navigate within a homotopy class, because there's no way to measure which one's shorter from different homotopy classes without another sensor. Yep.
When you have different options on different non-permitted gaps, do you know how far they?
No.
How far? No.
Nothing.
So you can choose.
You just pick whichever. They all look the same.
So it's not the optimal path.
You cannot formulate an optimal exploration problem the way it's formulated the way it's done right now. It does not make sense to make an optimal exploration problem. If you want to add the distances and try to make some kind of geometry question like that, maybe. My goal was minimalism, so I wanted to give the robot as weak information as possible and show that you could still do distance optimal navigation. Here's another problem, and this will remind you of computational geometry quite a bit. Remember this one, the permutation sensor from a few days ago, last week? So we have this is a relational sensor, right? The robot's there, it does a counterclockwise sweep, and it gets an observation like this, which is the cyclic ordering. And be careful, it's cyclic. So 4, 3, 5, 1, 2 would be the same. It doesn't matter which number I started with, it's a cyclic permutation. If you have that sensor, and if you have some points in the plane, we ask the question, what can you learn about the arrangement of those points? And what kind of task can you solve? Well, it's very interesting. So we have, again, a motion primitive, because we're doing planning. We say the landmark locations are unknown, and we have a primitive that says go to landmark objects. So here we can say go to 9. Just like chasing the gap, we can go to a landmark. And here's one thing we can do. While we're moving to 9, we can notice which landmarks are to the left and which ones are to the right. If you have that kind of information, what can you do? Any ideas? If I have a bunch of points and I look at an array, I take 1 point, I take 2 points, let's say, and I shoot a ray through them, and then I can answer the question, which points are to the left of that ray and which points are to the right of that ray. What kind of computations can I do? Convex hulls. Very nice, yep. So we showed that you can learn the arrangement. This is also the arrangement of lines in dual space, right? In computational geometry. So we showed that that you can figure out, you can answer any question about convex hulls. So for any subset of the landmarks, you can answer the question which other landmarks are inside their hull or outside. For example, for any triple of landmarks that forms a triangle, you can ask which landmarks are in the triangle and which are out. And then we made some basic controlling strategies, like you can go around the boundary, because you can go around the convex hull of the whole collection and navigate around that and do different kinds of things like this. So it's very nice. So you can say that the robot learns this dual arrangement. This is also very closely related to order types. You can describe it nicely with that. If you like oriented matroids, it's all that same family of stuff that's in here. So very nice structure. We showed this problem to a well-known computational geometer, and he right away, very good person, he right away said, no, this is impossible because the realizability problem is NP-hard. If you're given some collection, you want to determine whether or not, if I look, for example, if I do some kind of sweepings of this and I look at the orderings of the points, to determine whether or not it's valid. In the dual space, for example, I have an arrangement of lines, and I want to look at sequences of lines that must exist when I sweep across from different directions. And then I ask, is that realizable? That's a very hard problem, but, NP-hard problem, but it turns out we do not face the realizability problem here. It's actually quite straightforward because it is realized because these are points in the plane that are produced in these measurements. So we do not have to decide whether or not it's realizable. We're taking measurements from a realized system. So it's actually a subtle difference that makes it very efficient for us. And it tends to cause some colleagues to think that maybe it's not possible, but it is quite possible. Nice. All right, so that's all for that one. Any questions? Just want to show that's landmark-based navigation. It's a very important branch of robotics, landmark-based navigation. Here's a very basic thing we can say about it. Once again, learning some basic structure, using some basic structures from computational geometry. Oh, yeah, I think it's right. Bug algorithms. Has anyone heard of those? Yeah, no, that's nice. Some people have heard of that. That's nice. They're very cute, right? This goes back to Lemelsky's group. Lemelsky and Stepanov are the first people to do that. A lot of other folks have looked at these problems over the years. Strategies like this. So I want to get from an initial to a goal. In this case, the free space is unbounded, but the obstacles are bounded. So that's inverted from the standard motion planning problem. Bounded or co-bounded, one or the other has to be bounded. Well, should be. So here's a very simple strategy. I believe this one is one of the original ones. What's that?
Bug 2.
This is bug 2. Very good. You even know which bug number it is. That's this one. I can't remember them anymore. It's in my book, so I do at one point in my life. So that's why I wrote the book, so I could write everything down so that I could forget it. Right? So you go this way, and then when you hit it, you try to go to the goal, right? And then when you hit an obstacle, you're not given the obstacles here. When you hit it, you do wall following, and you look at the distance to the goal, and you agree to go all the way around to the start, and then go back to the place where the distance was the lowest. And then from there, you leave and keep going until it happens again. And then they prove some very simple bounds about what's the worst case performance of this in terms of the perimeter of the obstacles. I think this one's no more than 3/2 of the total perimeter of all the obstacles. It's this one. Plus the distance between xi and xg. I think that's what it is. So it's kind of some straightforward analysis. This was a very nice attempt at minimalism. They were doing this at the time of the great popularity of the piano movers problem. In the 1980s. Trying to make an argument that you should do it with limited sensing information. However, in doing this problem, because you always have the distance to the goal, and because of the information they're keeping track of here, it turns out if you read their papers and look at their models, there's enough information in there to reconstruct an exact representation of the obstacles. I never liked that very much. I guess they kind of pretend the robot's memoryless or something, but still, there's enough sensor information there because you know exactly where the goal is and you know what direction it's at. So they say you can measure the angle to the goal and the distance. Well, guess what? That's polar coordinates. So that means I can always just make a polar coordinate representation of all the obstacles. So I didn't like that too much, but I like this philosophy, though. It's nice. So we made an approach where we called it the intensity bug, where we have unknown obstacles here with piecewise analytic boundary so that we don't have infinite numbers of wiggles and stuff. Each obstacle boundary has finite length, and we have something called a tower which sends out a signal, like a cell phone tower. And the robot has very limited sensors, which I'll talk about in a bit, and we command the robot so that it reaches the tower. That's the idea. We command the robot so that we say, go to the tower. Here's the sensors. We have a contact sensor, our boundary sensor. Remember that one? You have to go back and remember our virtual sensors now, and the catalog of sensors that we did. That was kind of boring, I know. We did 50 or 100 sensors, I don't remember. But, so that's one of them. All it does is detect whether or not the robot's on the boundary. We have a tower alignment or gradient sensor. So all it tells it, is whether or not the robot is aligned to the tower. Is it facing the tower? You could do this with a directional antenna, for example, right? It looks like a satellite dish, remember those? If you move it just right and point it at some tower, if you're receiving a signal that way, you'll get a maximum in the signal, right? When you're pointing that way. Sometimes we want a gradient sensor, I'll explain why, but it's just very similar. It's a direction of maximum increase. And we want something, I'll call it a transformed signal intensity sensor. I gave you examples of field-based sensors, right? Vector field-based sensors. And I said maybe you could have intensity. And I even said maybe you could have a monotonic function that you don't even get to have. Remember I showed the signal meter? This is like the signal meter on your when you're trying to align a satellite dish. It'll show you that the intensity is going up, but you're not sure exactly how much power the tower has and stuff like that. Because if it's too powerful, you can determine exactly how far away the tower is. And I will not give you that information. But you do know when you're getting closer to the tower. That's different from knowing how far away the tower is. Right? It's like, I don't know, people always imagine you can do that with a Geiger counter, like these radioactive, it goes deep, 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 you're walking around and you hear it getting larger. It's kind of like that. All right. So, M, the function here, has one local maximum, and that happens to be the global maximum, and it's at the tower. I'm going to assume that. I'm going to assume that M itself is not given, and I'm going to assume two different cases for the level sets of M. The level sets will either be symmetric, which will make nice circles. In other words, from any direction around the tower, it's going to give the same intensity, if you're the same distance away. I still don't know how far away, but that's one assumption, is that it could be symmetric. Or we'll look at the asymmetric case. So here's the possible actions for the robot. I can say go forward until either the boundary of the environment is hit, the tower is hit, because that's your goal to hit the tower, or there's some kind of local intensity maximum. I'll explain how that can happen. Based on the direction that you're going, you can still hit a local maximum. Even if the function itself has only one global/local maximum, it may be the case that your direction of motion might cause a local maximum. I'll show that. So that's one, go forward. That's you forward there. You follow is follow the boundary of the environment until you detect a local maximum. So I'm going to assume these primitives can be done. And you orient, which is rotate until you are facing the tower or the local gradient of the radio signal. Like I said, it's like aligning the antenna. So here's how the plan works. So you move to align, so you rotate until you're aligned with the tower, then you go straight until your contact sensor tells you hit the boundary. Then you move around the boundary until you detect a local maximum, and then you go forward again. You realign and go, and you just keep doing this. If I do that, what does that look like? What's the filter? For that strategy, what is the filter? Well, the state space we know, right? There's the state space on the top. Unknown environment, fancy ease, and R2 process 1, that's this one again, right? Because I do not know the position and orientation of the robot. But let's look at the information space. I would say there are 3 sensors, that's what I gave you. Oh no, sorry, there are 3 observations I want to keep track of. And they're all based on intensity. So if there's one sensor that I'm mainly using here, which is intensity. The contact sensor gets used just to change actions. But for my information, for my strategy or the plan that I'm going to make, I use just the intensity observations. There's three things I need to remember. So just imagine I have like 3 registers that I remember. Okay, these are real numbers, and real numbers are so large that I can store all of Wikipedia inside of a single real number. I know that. So if you want, you can make a precision-based version of this if you like. But really, there's just 3 numbers, and we can make a quantized version if you want to argue about whether or not real numbers are too big or something. I think computational geometers use real numbers sometimes too. But it's okay. All right. So it's like three coordinates. The current observation, in other words, the current signal intensity on my meter. I want to know what the intensity was the last time I hit the obstacle. So if I'm moving along the obstacle, I want to remember the intensity when I got there. And then I want to know if I leave the obstacle and go forward, I want to know the intensity that I left with. So those three are all you need. Wait a minute, the first one you don't even have to remember, right? Because that's your current sensor reading. So actually your memory only needs to have these two. If you think about what's in the memory. The strategy will depend on all three. So that's what you have for that. And like I said, with those pieces of information, I argue that we have enough to execute the strategy. So the filter only needs those intensities to decide where to go next and when to switch between these policies. If we have, let me see. Sorry, I keep switching back and forth here. In this case, I assume the level sets are circles, concentric circles. So that's the symmetric case. If you do not have that case, you cannot align directly to the tower. And all we assume is that you can align to the local gradient. So here's an example where this is the way the signal might look. And so what might happen is you try to move, you align yourself in the direction where the gradient is the largest. I'm sorry, you align yourself in the direction of the gradient, which is the directional derivative that's maximized, right, over all directions. And when you do that, you might move for a while, but then you'll experience a local maximum. If you do, the procedure is to realign to the next gradient. It turns out that's a well-known optimization method. It's called steepest descent with line search, and it's known to converge. So we can prove that that converges as well. The number of steps is hard to characterize. Like I said, you can do these strange motions here to get to the tower, but nevertheless, we still get convergence. Someone sometimes asks for this. Oh, if you can use optimization methods, why don't you use conjugate gradient descent, which is known by optimization people to be much more efficient than this? Anybody know why we don't?
You cannot take the low derivatives.
Yeah, very good. Yeah. If you have a function you want to optimize, you might take derivatives, right? You need second-order derivatives for that. This one's only using the gradient. There's no way it can get second-order derivative information unless it moves around in a local pattern and tries to estimate higher-order derivatives. I guess it could try, but we don't even give it that kind of metric information, right? So it cannot do that. So we're forced to use what's considered an inferior optimization method that exists in the literature, but people don't know it very well. I have colleagues who do optimization and numerical methods, so I just ask them, does this exist? And they said, yes, it's this name. And that's it. So it's very interesting.
So,
Yes?
does it guarantee to have an answer every time? I mean, maybe it'll start somewhere.
This one will not get stuck. The function M has one local maximum, which is at the goal, at the tower. So and because of that, and let's assume the function has some nice properties, like I do not want the function to have an infinite number of variations and stuff like that. So if the function has, gotta be careful what I say here. I'm not sure if it's just bounded variation that's needed or some kind of it could be that it needs to be piecewise analytic. I need to sort of look at the precise conditions, but there's not a problem of getting stuck in local maxima here or minima, local maxima here.
I have an example that when you have a local maximum, maybe be in a loop. I mean, get to
Okay,
local maximum and
okay. Let me show you something. So if the tower is reachable, you will reach it with this method. If the tower is not reachable, you can get stuck. So what you cannot do with this robot is decide whether or not there's a tower. Let me show you that example. Maybe this is the kind of thing you're thinking of. So for example, if you're like this, going around an obstacle, and you're trying to get to the tower, this algorithm will fail because it keeps trying and trying, and it never knows if it's done, because maybe there will eventually become a place where it can go. After just another one or more, after just another variation, there might be a place where it can leave and go to the tower. Or it might say, well, maybe I keep going around and around, and it cannot detect that it's come back to the same place again. So in this case, it does get stuck. But if the tower is reachable, it will converge to it. Because whenever it leaves, it's always leaving the obstacle and improving. It leaves when it's improved its intensity. That's why it has to remember, I probably forgot to mention this, when it enters the obstacle, it remembers the intensity it saw there, and it leaves only when the intensity is better. So it leaves at a local maximum along the boundary and when the intensity is better. Yeah. Yeah, so that's an important step. That's why I forgot to mention that, sorry. That's why you have to remember this information, the observation, the intensity when the obstacle was last contact, when you got there.
What if the flower is between two? Can I stay with the picture?
Sure.
Last slide, 45. How is the direction of the spark?
For that one?
One more. Previous. Yeah, there. That's fine.
Yep.
You could go straight and on the other side of this.
Yeah, it doesn't matter. I think in this case we just made a rule that it always turns right.
My example at first was this, and when you start from here, you will go here, and you then go.
Oh, right. Yeah. But you're further away.
Yeah.
Yeah, so exactly the thing I forgot to mention, you figured out, and then that remembering that one in your. So that's right. You see that by doing this approach, we're getting right down to the mathematically necessary conditions to achieve a task, which I really like. I make a mistake and I forget to mention that, and you show me no, it doesn't work anymore. Right? It's exactly where it breaks, which I like that. Right? So that's why it's here. Very good. So it's interesting. Here you cannot decide. There's a generalization of this that's very interesting. What happens when you have multiple towers? And you can start to learn, like with two towers, you can learn some kind of two-dimensional manifold because you have two intensities. So you're learning some kind of manifold, and the question is, what tasks can you solve with that? Right? You can build a kind of representation of the environment that's geometric but highly distorted compared to the actual environment. So anyway, these are interesting things to think about. Other questions or comments about this one? Sensorless manipulation is another example. I wanted to put something in that fits very nicely with Frank's presentations. And so how does that fit? This is the old work of Mason and Goldberg when you're squeezing parts, right? So this was covered, right? So what happens there? Well, here the state space, all I care about is S1, right? Just the orientation of the part. And then I have these different squeezings I can do. The information space, well, it's a subset of this probably for this problem, but in general, it's a power set of X. I think the way things work out for this, power set of X is fine. I don't want to describe which sets are not in there, but that's too many, but they're all included in there. Power set of X. A plan looks like a sequence. Remember that I said sometimes the path in the information space may be predictable. It's predictable here because there's no more sensor information than you get during execution. The gripper probably knows when it's done squeezing, so it might have a force sensor. That's implicit here. So is it sensorless? I'm not sure. It needs to know when it's done. And also there needs to be some way to know how to rotate the robot squeezer exactly so that you get different orientation. So assuming you have some sensors inside of there that execute these actions, after that you don't need any more sensors. So you just have a sequence of these actions that perform the squeeze operations. And as Frank was talking about, you look at this diameter function and the local minima of that tell you the possible orientations of the part after a single squeeze. And so you just have to go and squeeze once, and you reduce the uncertainty from all possible orientations, all of S1 initially. After one squeeze, you have a finite number of possibilities. You do a few more squeezes and you're done. You get it down to a single orientation. Well, or in this particular case, you have some symmetries, rotational symmetries. So it's just down to a small finite set. As I said, I think Frank showed these kind of things, but I just wanted to say that the sensorless manipulation fits in here perfectly as well. And so these things I think were shown. So It's interesting that even though the particular movie is different during execution, remember that in the information space, it plays out the same way every time. Because we can see the orientation of the part, but the sensor cannot, right? There's no sensors that can see that. That's why it's a path in the information space. Same for the pursuit evasion algorithms, the visibility-based ones. It looks the same every time if there's no evader, right? It just moves in a way that guarantees that there could not have been an evader. All right, I'm going to get to the last part, and some of you have seen this already, and I apologize for that. If you're from University of Tehran or Sharif University, you may be tired of seeing this, but I want to show this part, which is the newest research that I've been interested in, and it continues down this path of minimalism and trying to make kind of minimalist systems, and it involves some experimental stuff as well. So I'll show a little bit of this, then I will take a break, and then I will finish the course up. Remember this filter, right? It only has 2 bits, there's 4 states in it, and it keeps track of whether or not the robots are together. Well, we used a very important assumption to make this. This one uses the same assumption. Visibility-based pursuit evasion. And this generalization to shadow information spaces uses the same assumption. What was the key assumption for reducing the complexity or formulating this problem? What makes all of these kind of possible so that you can reason about it combinatorially? Remember the assumption? Well, that does show up for a lot of these, although there's no shadows here for this one, right? So, the main assumption was that the bodies move on a continuous path with unbounded speed, right? So very simple assumption, but that was critical to all of a sudden getting combinatorial representations, which is very nice, right? So I want to know, if I want to control bodies in the environment, what other kind of assumptions do I need now? This was a good assumption for making nice filters, I think, because it lets you reason about the information states in a combinatorial way. So I wanted to find some kind of assumption like that. So, like I said, for those filters, we exploited only motion continuity. So I would like to know, when we do actuation, and I still want to do minimalism, what can we do? Well, in the passive case, when I made those filters, I said to you, we would like to avoid state estimation. Right? Avoid estimating the state. Well, in the active case, I think I would like to also avoid doing system identification. In other words, I do not want to do system identification and state feedback like is often done in control. So if I'm not going to do system identification, you know what system identification is? Right? That's determining the equations of motion. In other words, it's the problem of finding this. X dot equals some function of x of t, u of t. And I think in this class I put tildes on those, right? So that's all. So finding that is very important in control theory. You can't do anything without that. You can do reinforcement learning kinds of things where you learn that while trying to design the optimal control. Well, that's fine. It's just a variant of optimal control to a large extent. An interesting one, though. And what is the key new property? Well, I'm going to call it wildness. That's the thing I'm looking for. That I feel like is as fascinating as motion continuity was for making these combinatorial problems of pursuit evasion and other things like that. I feel like wildness is a nice property that's going to let me get away with using very simple filters, and it's going to let me avoid system identification. So I'm going to avoid a lot of the things that control theorists want to do too, like state feedback and stabilization and stuff like that. Let me show you our simple robot. We get to have videos now. Isn't that nice? So just in time for nearly the end of the class. So this is our intelligent exploring robot. It has a lot of minimalism in it. Can anyone figure out what strategy it's executing? Let me move the speed up twice. This is double speed here, just to kind of see it go a little more. It will try to hit all of the places. It's like it's trying to escape or something. It's quite what I would call wild. It gets in there and it finds everything, right? Very nice. Systematic exploration robot. Quite beautiful, right? All right, so what kind of system is this? Let me show you what kind of system this is.
It comes up with the complete map of the environment.
I will show you. It's a good question. Perfect. Any other questions like that I will not answer? Yes?
Actually solid boundaries with, for example, color edges or...
Yeah, maybe. Any other ideas of what it's doing? Except for those of you who are from Sharif or Tehran University. Contact sensors, maybe. So let me tell you about this robot. There's no map given to the robot in advance, so unknown map. It cannot measure any position information, so no X and Y and no theta. It doesn't have that, ever. I did not do system identification like I promised, so I have no idea of the mechanics of this. I do not understand its equations of motion. Terrible. I don't understand. There's no sensors. There's no sensors in the robot, and there's no sensors outside of the robot. There's no computer. There is no digital circuitry at all. There's one circuit. Let me show you the circuit. It looks like this. If you have electrical engineering background, the circuit looks like this. This is a power source, like a battery. I think it's a battery, something like that. I can't make them anymore too well. And then there's something called a motor. And that's it. So that's the entire electrical system, including all non-existent digital circuitry in the robot. So I brought one with me. Right. It's in nice University of Illinois colors, orange and blue. Here's the robot. It has the power source is what we call a AA battery. What's the name of this battery you're on? That one, yes. All right. And so, pen battery, perfectly fine. That's all it is. You see the motor going around, right? That's all. And so then we put it down. And then it will just start exploring. Just like in the video, no problem. It likes feet a lot, so it always tries to find feet.
We can't see.
I understand. I have an idea. During the break, why don't we take a break and we can play with it? Okay? All right. So let's take a break and then I will finish the last part of the course. It's called a weasel ball. That's the weasel. It's supposed to look like the weasel is chasing the ball, but if you remove the weasel, it's much more beautiful. So anyway, that's all we'll show that. Let's take a break and then we'll have, yes?
What is the aim of this robot?
The aim? Let's talk about that during the break. Anybody else? Yes.
Gift.
What? Gift? For it? Well, this, I will leave it to my organizers of the winter school. They can decide what to do with it. All right, let's take a break. Thank you.